Dear students, today I am going to discuss about the simple harmonic motion from module 5 of engineering mechanics. So before discussing about the simple harmonic motion, let's look into what do you mean by mechanical vibrations and what are the different types of vibrations. So if you are taking vibration, so vibration is concerned with the oscillating motion of elastic bodies and the forces which are associated with them. So the mechanical vibration, it is the oscillatory with regards or it is concerned with the oscillatory motion of the dynamic systems such as machines, etc., machine parts, etc. So if you are taking the vibration of mechanical system, it occurs when a system is displaced from its position of stable equilibrium or mean position. Some stable equilibrium will be there for any system, and if it is disturbed from that system, some vibration will be occurring. So the system will be always having a tendency to return to its equilibrium position due to action of some restoring force. So this restoring force can be either elastic or gravitational. For example, in the case of spring, you will be having an elastic restoring force, whereas in case of simple pendulum, it will be a gravitational restoring force. Then if you are taking the elements of a mechanical vibration, mainly there are three elements: inertia element, compliance or elastic element, and a damping element. So here I am taking or I have taken a spring and mass arrangement. So here this mass will be moving to and fro on the application of some excitation force. So this mass represents the inertia force. So it oscillates or vibrates under the action of excitation force. Then this spring represents the elastic element. It will be storing energy during the vibration for continuing the vibration. And we are having a damper here. So this is the damping element. So it will be consuming and dissipating energy, and hence it will be resisting any resistance to vibratory motion. So due to the presence of this damper, what happens, the vibratory motion will be having a damping effect and it will be dying off eventually. So these are the elements of a mechanical vibration. Then if you're taking the classification of mechanical vibrations, so based on the direction of motion of vibrating body with respect to elastic medium and based on the nature of stress induced in the mounting medium, you can divide the mechanical vibration into three types, that is longitudinal vibration, transverse vibration and torsional vibration. So in longitudinal vibration you will be having to and fro motion parallel to the axis of shaft in transverse vibration, perpendicular to the axis of the shaft, whereas in torsional vibration you will be having a twisting movement with respect to axis of the shaft. Then if you are taking the stresses developed, you will be having compressive and tensile stresses developed in case of longitudinal and transverse vibration, whereas shear stress in the case of torsional vibration. So here for example I am considering a shaft and a mass arrangement. So at the end of the shaft you are having a disc or mass connected here. So if you are taking longitudinal vibration, this mass will be moving like this. A to and fro motion will be there, that is parallel to the axis of the shaft. So due to this to and fro motion, what happens, there is an elongation and shortening occurring on the shaft. So due to that, tensile and compressive stresses will be developed in the shaft. Then transverse vibration, perpendicular to the axis of the shaft, some motion will be occurring. So it is transverse vibration. So here there will be bending of shaft occurring. So there will be compression and elongation occurring here. So due to that, tensile and compressive stresses will be occurring. In the case of torsional vibration, this disc will be moving parallel to the rotating parallel to the axis of the shaft. So there will be a twisting moment occurring, or twisting moment will be occurring. So due to that, some shear stresses will be induced in the shaft. So these are the three classifications based on direction of motion of the vibrating body and based on the nature of stresses induced. Then we can have free vibration and forced vibration based on how the oscillation is undertaken. So in the case of free vibration, the system will be oscillating under the action of the forces which is inherent in the system due to some initial disturbance. So here you will be having some initial force that will be causing the vibration, but this initial force will be removed and after that also the periodic motion will be continuing. So that is the main thing. The periodic motion will continue even after this force that causes the oscillation was removed. And this vibration will be eventually dying out due to the loss of energy in the system. In the case of force, the example for free vibration is simple pendulum, spring, etc. So if a simple pendulum, if you are initiating the vibration, what happens? It will continue the vibration for some period. Similarly, in the case of spring also. Then if you're taking forced vibration, it will be taking place under the action of excitation, some external excitation force. So here the periodic disturbing force will be acting on the system and the system will be vibrating at the frequency that is equal to the frequency of this excitation force. So here this excitation force will be acting on the system for creating that periodic oscillation. So the example is the vibrations in the building caused due to earthquake, etc. are the examples for forced vibration. Then another classification is damped vibration and undamped vibration. So in the case of damped vibration, we are having some external resisting force that is acting on the vibrating object. So eventually the vibration will be damped off. Then in the case of undamped vibration, no such resistive force is acting on the vibrating object or system. Next is degree of freedom. So degree of freedom is the number of independent spatial coordinates that is required to define the configuration of a system. So in order to determine the degree of freedom, we must consider how many distinct ways the given object can be moved. For example, if you are considering a rigid body in a plane like this, so it can be moved in three ways. It can be moved in x direction, can be moved in y direction, and can be rotated about the centroid. So it has three motions permitted. So it has 3 degrees of freedom. And if we are considering a rigid body in space means you are having three coordinates. So you are having three translational motions along these three coordinates and three rotational motions about these three coordinates. So you are having total 6 degrees of freedom. Three translating motions and three rotary motions. So we can go to simple harmonic motion. So if you are taking simple harmonic motion, it is a motion which is actually periodic motion. So that repeats after equal interval of time. So for any periodic motion to be a simple harmonic motion, these two conditions have to be satisfied. That is, acceleration of the particle should be proportional to the distance of the particle from mean position, and the acceleration of the particle should be always directed to the mean position. So if these two conditions are satisfied for a periodic motion, then it becomes a simple harmonic motion. So you see this example. So here we are having a simple pendulum. So this is the mean position. So this is the stable equilibrium if the mass is kept here. And if we are moving the mass to an extreme position, that is n, then we are dropping that. What happens? This simple pendulum will be oscillating like this, and this acceleration, it will be always directed to the mean position because this mass will be always tending to achieve this mean position. So acceleration will be always directed to this mean position, and this acceleration will be proportional to the distance from mean position. So you can move this mass to this position and to this extreme position also, but the acceleration will be more at this extreme position when compared to this position. And if you're taking a spring, here also you see, if we are taking a spring, this will be the mean position of the spring, and if you are stretching that spring, what happens? It will be moved out from the mean position like this. So if we are extending that to a longer distance, what happens? The acceleration will be more, or the force at which it will be coming back to its mean position will be more. So as the distance from the mean position increases, what happens? The acceleration will be also increasing, and the acceleration will be also always directed towards the mean position. So this is how the motion of the simple pendulum will be occurring. So like this, it will be moving like this, you can see. from the mean position to the extreme position. And if we are checking the movement of the spring, it will be like this. From mean position, this will be the mean position. Then from here, it will be oscillating to and fro like this. And the acceleration will be always directed to this mean position. So these are the two conditions that have to be satisfied for a periodic motion to be a simple harmonic motion. The acceleration should be proportional to the distance from mean position and it should be directed towards mean position. So the different terms used are these: amplitude, oscillation, frequency, time period and beat. So for explaining that, I will use this this figure. So here we are considering a particle P that is moving around a circular path which is having a radius r, and it is moving around at an angular velocity of omega radians per second. So the initial position of the particle will be A. So if you are representing that as a waveform, it will be like this. So at time t, the position will be A. Then as time increases, this particle will be moving from A to C, and C is the extreme position. So it has moved pi by 2 distance. So this is the position C. Then after that, it will be moving from C to B, that is from pi by 2 to pi like this, and again from pi to 2 pi like this. So this will be one cycle. From A to A, it will be one cycle, and this is the mean position, and these are the extreme positions. So amplitude is the distance of the extreme position from mean position. So this will be the amplitude, or this one, anyone. It will be the amplitude, and the time taken for moving from A to A will be the time period, that is for one cycle. Time taken for one cycle will be the time period. So amplitude is the maximum displacement from mean position. Then time period is the time taken for one oscillation, and frequency is the number of cycles per second. It can be represented as 1 by Tp, that is 1 by time period. Next is oscillation. So for describing oscillation, so you see you are taking the movement of particle along the circumferential direction. And if we are projecting that to this diameter, suppose this is the position of P at t equal to 0, and the projection will be O on this diameter CD. Then the particle will be moving along the circumferential direction from A to here. Suppose if the position is here, its projection will be coming on the diameter at this position. Then again P has reached here. Its projection on the diameter CD is here. Then it has reached C. So what happens when the particle moves from A to C? Its projection will be moving from O to C on this diameter CD. Then the particle moves from C to B. So when the particle moves from C to B, the projection will be moving from C to O. Then when the particle moves from B to D, the projection will be moving from O to D. Then the particle will be moving from D to A, the projection will be moving from D to O. So as the particle moves from A to C, C to B, B to D, D to A to complete one cycle, the projection of the particle on the diameter will be moving from O to C, C to O, O to D, D to O. So it makes one oscillation. Okay. So the oscillation is the motion of projection of particle along the diameter, and half oscillation is known as beat. So for derivation of velocity and acceleration of simple harmonic motion, so consider the same, that is a particle is moving along a circumferential direction or around a circle which is having a radius r, and let P be the position of particle at any time t. Then it is inclined at an angle theta with x-axis. Let M be the projection of the particle on x-axis at time t, and M dash be the projection of particle on y-axis or vertical diameter at time t. Then x is the distance of M from main position O. Then x dash is the distance of M dash from O. So we know that angular velocity omega, it is represented in radians per second. So it is equal to the ratio of angular displacement to the time taken. So here omega is equal to theta by t, where theta is the angular displacement and t is the time taken. So for one oscillation, the particle will be moving like this from A to A. So the total angular moment will be equal to 2 pi. So for one oscillation, the time taken will be equal to time period Tp and theta will be equal to 2 pi. So Tp becomes 2 pi by omega. Then here x can be written as x is equal to OP cos theta. So OP cos theta, OP is equal to R and theta you can write it as omega t. So x becomes R cos omega t. So velocity can be written as velocity is equal to dx by dt. That is, velocity is the derivative of x with respect to time. So if we are differentiating this x with respect to time, it will be becoming cos omega t. If it is differentiated, it will be becoming as minus sin omega t. And so the multiple of t is here omega. So it becomes minus r omega sin omega t. So V is equal to minus R omega sin omega t. So negative sign indicates that as t increases, x will be decreasing. So t means t is 0 here, then it will be increasing. So as t increases, what happens? This projection x, if particle reaches here at time another greater than t. Here time is t we have considered. So as particle reaches here, what happens? X will be coming here or m will be coming here. So x will be this distance only. So x has decreased. So as time increases, x will be decreasing. So hence this negative sign will be coming in the equation. So if we are taking the magnitude alone, it will be r omega sin omega t, or you can write it as r omega sin theta. So sin theta is equal to Pm by OP. So it is equal to what? OP is equal to R. Pm you can write it as root of R square minus X square by applying Pythagoras theorem here. So equation becomes V is equal to omega root of R square minus X square. So that is equation for V. Then acceleration can be taken as dv by dt, that is differential of velocity with respect to time, because acceleration is change in velocity by rate of change of velocity. So it becomes d by dt of minus r omega sin omega t. So if we are differentiating that, you will get it as minus r omega square cos omega t. So A is equal to minus r omega square cos theta omega t. You can write it as you can write it as theta. So it becomes cos theta. So from figure cos theta is equal to x by r. So minus r omega square x by r. So acceleration A becomes minus omega square x. So from this you can see acceleration is proportional to x, that is proportional to the distance from the mean position. So that was our one condition for the equation, sorry, for the motion, periodic motion to be simple harmonic motion. Then we can see acceleration is always directed to the mean position. That is, as t increases, x decreases. So that means it is always directed to the mean position. Then at x is equal to 0, the velocity becomes maximum. So you can write Vmax is equal to omega into root of r square minus x square. Here x becomes 0. So it becomes omega root of r square minus 0, or Vmax is equal to r omega. Then the acceleration becomes maximum at the extreme position. So x is equal to r, that is at extreme position x is equal to r. So maximum acceleration becomes minus omega square r. Then for finding out the equation for omega, you can take the relationship between Tp and f. So time period Tp is equal to 1 by frequency. We already know that time period Tp is equal to 2 pi by omega. So 2 pi by omega is equal to 1 by f, or omega is equal to 2 pi f. So these are the equations for acceleration and velocity for a simple harmonic motion. So the problems can be discussed in the next video. Okay, thank you.